Started. Primarily today we would be closing. We'll try to close the discussion on the statistical sections that we were having, right? And in the last class we had been talking about. We had been quite talking about the statistical inferential part, right? So we had discussed about uh, what exactly a statistical exercise is and statistical inference is. So we have discussed about sampling distribution. We have discussed about estimation, and we have discussed about uh, you know. So we have discussed about the testing hypothesis. Right? So mostly what we were doing in the last class was involved around testing and hypothesis. So we had brought about the concept of an actual distribution. I mean an actual value and an observed value. So an actual difference, or I don't know, a significant difference, and uh, observed difference, right? So that is the part where with which we had ended our discussion in the last class. So we had talked about test statistics. We had talked about the errors, right? And we said that we had explored at a very basic level how a decision or a test decision is generally done. How is it that I would, like, if I am performing a statistical test, how is it that I can actually decide whether the particular test has been passed or it has been failed, right? So that is one discussion that we had yesterday. I mean, in the last class. So over here, having said about that, one thing we saw that to get on the statistical discussions done, right? What we need to know is we need to have a few important things. We need to have some few important inputs to have an idea about uh, observed difference, about a significant difference, and above all, to frame an idea about the testing procedures. Right? So, if I'm trying to test something, right, all I want to know is whether is it significantly different or whether is it just an observed difference from a given benchmark value. And that is all I want to know in the testing procedures. And for doing that, there are some important components that we require, right? So we had touched upon all those concepts in the last class. Today's session, we would be, framing a more concrete idea about the same, and from there, we try to bring out that how a proper testing procedure can be conducted, right? So basically, we start off with the hypothesis with which we had, like put in our discussions with. And it had begun on the fact that, so we start off with a null hypothesis that H0 is equal to, H0 is X bar equals to mean versus the alternate hypothesis X bar not equals to. So basically what we said is that, okay, so we saw that X bar is a good estimator for the population mean, right? Why? Because it is, above all, it is an unbiased estimator for the population mean. Similarly, what we also saw was that since it was an unbiased estimator for population mean, it was also a consistent estimator. Also, it was an efficient as well as a sufficient estimator. And assuming that the population is normally distributed, can we say that the X bar, if I look into X bar, well, can I say that this is more or less what the population mean is? Now, how do we zero down on that? So we can zero down on that by saying that X bar. So basis the value that I get to see in the sampling distribution of X bar. So basis that we can actually conclude that it would be something similar to the population mean if and only if the following conditions hold. And what are those following conditions? The condition is that if we test and we see that the difference between X bar and mu is not significant. So there may be a difference between X bar and mu, but there is, I mean, the difference that is there, that is not a very significant difference. All the X bars are more or less close enough to mu. So I need to distinguish that whatever the difference between the X bar and the population mean mu is, that difference is not a significant difference. So it's just an observed difference. Now, when I say it's just an observed difference, the idea is that the difference is observed because there are, the difference is observed because whatever difference is there is because of sampling fluctuations. There is no significant difference between the two, right? Now, over here, what we need to do is, so we need to test for the observed difference versus the significant difference. But the question that comes out over here is that what causes the observed differences, right? So what causes the observed differences? Hold on. So the question that comes out is that what causes the observed differences? The observed differences are caused by sampling fluctuations. So they are just caused because the sample size changes. Because of sampling fluctuations. Sampling fluctuations, right? So over here, what you have is X bar is equal to mu. So the entire idea of testing is to understand that whether in the differences that are being observed between say X bar and mu, or between say the right hand side and the left hand side, whether is this difference arising because of sampling fluctuations or not, right? So an observed increase and a significant increase is something which we have already defined, right? So we have seen that a significant increase is one which actually impacts the output, uh, which is so basically what I can see is that increase is an observed increase if it does not really impact the output. So therefore, the entire idea over here is that, so how do we do this distinction? To do this distinction, we require some important factors. One is a cutoff value or a critical value, one is an actual value, and the errors associated with it. Now, one very simple way of identifying whether a statistical test is passed or failed is that if the actual value of a test statistic is less than the critical value, then what happens is your test has failed. But again, if I have to define a critical value for a particular test, I have to take into account the errors that can possibly be committed. right? So there is this difference as well. So the question that comes out over here is that how do we do this distinction? How is this? How even is this distinction possible? Right? So let's explore these concepts first. And the part that we start off with is with the concept of a test statistic. So how do we know whether the sample mean and the population mean are significantly different from each other or not? So to do that, we'll start off by talking about the test statistic. Yes. So to your question, Preeti, if we take the significance level, right? So basically, the significance level is not the confidence interval, right? And it is taken not as zero point 0.5, but it is taken as 0.05 or 5%. So corresponding to a level of significance of 5%, the confidence interval is 95%, right? So that is on the error side of things. Now, what we do is we start off with the test statistic, because when you are actually doing something in SAS, right? SAS will report the test statistic as well, and along with it, it will represent, or it will talk about, or it will ask about the, or it will report the level of significance, the p-values, etc. Okay. So again, let's start off with the concept of the sampling distribution. So the basic idea of sampling distribution was that you have these multiple samples which are collected. So over here what we have is first of all a sample number, two, three, x bar. So for the first sample, the sample mean turned out to be x bar 1. For the second case, it turned out to be x bar 2. For x3 turned out to be x bar 3. Then it turned out to be x bar 4, and like this it went on to have x bar 5. So basically over here what we have is frequency f1. From there what we have is frequency f2, f3, like this. Here is f5. And from there what we can construct is the relative frequency. Then what we have is f2 by n. Like this we have up to Okay. So now over here, the next thing that we have is as follows. That now from here, what we can compute is the expected values of x bar. Now, since expected value of x bar since x bar is an unbiased estimate, right? Therefore, what we get to see is that expected value of x bar is mean. Now, what I want to know is that how different are each of these means from this average value, right? So, if all the means or most of the mean have a very significant difference from the population mean, then we can say that yes, there exists a significant difference between the sample mean and the population parameter m. I mean population parameter mu. So over here, what we have is expected value of x bar equal to mu, and these are all the sample means obtained from each of the independent samples. So now, what I want to know is two things: that what exactly is the difference between this x bar and population mean, right? So basically, what is the difference between an x bar of a sample mean and from this mu? So it is nothing but x bar 1 minus mu, or similarly x2 bar minus mu. So this is what the difference is, right? So it's x bar 1 minus mu, x2 bar minus mu. Now comes the next question: how do I know that this, or how much is this difference? The reason is, in the last example, so when we talked about the mathematics test example, we saw that in one case, the difference of 3, I mean an increase of 3, was significant. But in another case, the same increase was not significant. Therefore, how can I be so sure that this difference that I am observing over here is a significant difference? So to assess this, what we need to do is the following. We need to look into the overall variation in the set of x bars. So to do this, we also need to consider the overall variation in the set of x bars. In x bars. So I'll study the overall variation. So how high or how low the variation is, right? So for example, say that this is the distribution that I have. So this is how my distribution of x bar would look like. So over here, so this is the overall spread of this distribution, right? So what we can see is that this distribution, or the values in this distribution, is spread towards the tails, right? So the spread is relatively higher. Now, higher the spread is, right? So then a difference of, say, suppose if I say that this is the difference of x units. So say I'm talking about this difference. Now since the overall spread is very high, Therefore, this difference would be relatively lower, or would be having a relatively lower impact, right? So the difference between x bar and mu is considered relative to the overall variation in the set of x bars, right? So over here, what we get to see is the following. So therefore, we also need to take into account the standard error of the distribution. Error of x bar. So similarly, say for example, I take another distribution over here, which has a much lower spread, which has a much lower spread. So then when the spread is relatively much lower, the impact of this small difference would be relatively higher, right? So to understand how high or how significant or how insignificant a particular variation is, what you need to do is, or what you need to assess is the following. What you need to understand is that how much is this behavior. So all you need to assess over here is that how much is the deviation relative to the overall variation in the data set, right? So how much is the deviation relative to the overall variation in the data set? So that is what we need to understand, or that is what we even need to assess. So therefore, if I want to understand the difference, whether the difference between x bar and mu is significant, that is x bar and the expected value of x bar is significant, then I will compare it with in relation to the overall variation in the set of x bars. So basically, my statistic would then be x bar I minus expected value of x bar I, x bar, divided by the standard error of x bar. So what I'm doing is I'm trying to assess the difference in relation to the overall variation in the set of x bars. So that is standard errors of x bars. And this statistic is called the T statistic. So T is equal to x bar I minus expected value of x bar in relation to the standard error of x bar. So whatever the difference between a mean and a mu is, that is to be assessed in respect of the overall behavior of the x bar. So overall variation in the x bar series, right? Right. So is this, and this statistic or this particular statistic is called the T statistic. Clear? So is the idea of this statistic clear, that why are we creating the statistic? How is the statistic being cleared? I mean created, and how does it help us test whether the difference between mu and x bar is significant or not. So is I mean are these concepts clear from these discussions up till now? Great. So once we have taken this, the next part that we talk about is the following. Now, how do I know that, or how do I take my decisions, or how do I decide on that? How do I decide my critical value? That is something that we need to know. So now the observed or the actual value of this statistic of this test statistic is identified, right? So this actual value is identified. Actual value of statistic is identified, or this is what we call the observed value. Right. So this is what the actual value is. So over here, now the next thing that we need to do over here is to identify the test, right? We need to create the critical value. Now the question that comes out over here is that how do I create the critical value? So defining the critical value is of a bit of a challenge. So let's understand that what is the critical value like, or what are the considerations that I need to have when I am designing the critical value. Critical value. So what is this critical value like? So for example, in the last class, when we had discussed about the critical value of the mathematics example, right, let's just reconsider those examples back. So what I had done was I had said that the cutoff marks was 40 and the full marks was 100, right? And the full marks was 100. And if you got a marks above 40, then you had passed the test. If you got a marks below 40, you did not pass the test. It's simple as that. So what do we do? So over here, now have a look into this critical value 40. So this critical value has been designed with respect to a given level of error, or with respect to kind of a permissible level of error. So basically what I'm saying is that when I'm defining the cutoff value, right, I am not committing to the fact that it will be 100% accurate. All I'm saying is that there is a permissible extent of error. There is a permissible extent of error. So the permissible extent of error. Now, having said that there is a permissible extent of error, the next thing that we need to talk about is, so basically there are two things. So when you are talking about in terms of critical value, you are also simultaneously talking about a permissible error. You are also specifying an error, and to that what you have is a observed error. What to that what you have is an observed error. So then I also have a observed error. Right? Say suppose I obtain a marks which is less than 40, and my marks is uh, 25, right? So over here, the permissible extent of error for the pass was, or acceptable error was, 60%, right? Permissible error was 60%. But what happened is I have actually committed an error of 75%. So if I have committed an error of 75%, which is more than 60%, then what happens is that my actual value of the statistic, that is my actual marks, is below the cutoff marks, because the cutoff marks was decided with respect to a permissible extent of error. And what I see over here is that with this permissible extent of error, that is the permissible extent of error is 60%, and the cutoff marks is 40. So over here, in this case, what you get to see is that this 25 is the observed or the actual marks, and hence the actual error committed was 70%. Therefore, the actual or the observed error is more than the permissible error, and hence I fail the test. However, if I had obtained 55, so instead of 25, if I had obtained 55, so the permissible error was 60, right? But the actual error committed was 45%. Therefore, the actual error is lower than the cutoff or the eligible error. Hence, you see that I have passed the test, right? So basically, a similar concept of error and critical value exists in this testing hypothesis case as well, right? So basically, when I am defining a critical value of a test statistic, I just cannot define any critical value, or neither can I choose a perfect value as a critical value, right? I have to always consider certain proportions of errors into my model. And when I do this, when I take into account this kind of a consideration, what I end up with is two concepts of errors. Concept number one, the first concept that we come up is with type 1 error. The first type of an error that we come across is the type 1 error. And it is this error, the type 1 error, which plays the most important challenge, and which plays the most important role in taking testing hypothesis decisions, in taking decisions of testing hypothesis. Clear? So it is these errors and the measures of errors, the possibility of errors that are considered over here is extracted from this type 1 error. from this type 1 error, we will draw out two basic probabilities of associated with the type 1 error, right? So one of them would be the level of significance, the level of significance, and the next would be the p-value. The p-value. Now, the level of significance will be, or it is the maximum, permissible error, and the p-value is, and the p-value over here is the actual probability of committing the type 1 error. Okay. So over here, we now the next thing that we need to do is we need to define what this type 1 error is. So there would be another error which is called the type 2 error. And from there, we'll talk about the level of significance and the p-values, right? So these are some of the, so this is some of the ways through which we will try to assess the testing procedures, right? Just give me a moment. I'll just be back and we'll continue it from there. Okay. So we'll start out by talking about the type 1 and the type 2 errors. However, throughout our discussions, we'll mostly be focusing on the type 1 error. So over here, what we have is H0. So H0, as we know, is the null hypothesis, right? And my null hypothesis over here is the sample mean is equal to the population mean, which would essentially mean that, or which essentially implies that whatever difference I can actually observe between x bar and mu is nothing significantly different. So, and this is the alternate hypothesis. Now comes the question that how do I know that, or when do I commit an error? Now, to assess whether I'm committing an error, right, and or whether I'm not committing an error, so we can actually use the following table, the following cross tabulation table over here. Over here, what we have is H0 true, and over here, what we have is H0 true. This is accepted, and this is say rejected. over here, if you see H naught is true and it is accepted, so that means this is correct. Over here, H naught is true, H A is true, and it is accepted. So that is correct. However, over here, H naught is true, but it is rejected. And this is where the concept of an error comes out. The next part, what we have is that the HA is true, but it is rejected. So again, there is this error, right? So over here, so if you are, accepting a true null alternate hypothesis, that means you are rejecting a true I mean, if you're accepting a true alternate hypothesis, you are rejecting a true or you are rejecting a false H0. On the other hand, if you are actually rejecting a true null hypothesis, then that is called the type 1 error. So this is called the type 1 error. error. And type 2 error is accepting a false null hypothesis. So if your null hypothesis is false, I mean accepting a false null hypothesis as in type 2 error is accepting a false, yeah, it's an accepting a false alternate hypothesis. Rejecting, but type 1 error is rejecting a true null hypothesis. So if there is a true null hypothesis and you are actually rejecting it, then it is called a type 1 error. And if there is a false null hypothesis and you're accepting it, then that is called there is a false alternate hypothesis and you are accepting it, then that is called a type 2 error, right? However, over here we would not be focusing on the type 2 error. All we are considering on is the type 1 error, because the entire testing procedure would be based out of or would be based on this type 1 error. So what is this type 1 error? The type 1 error is nothing but rejecting a true null hypothesis. Rejecting a true null hypothesis. Null hypothesis. Right? So if I'm rejecting a true null hypothesis, that means there is something which is insignificant, but I'm claiming that difference to be significant. So this is where this concept or this rejecting a true null hypothesis comes in, and it is the probability of rejecting the null hypothesis is what which drives the decision rules. So the probability of type 1 error, probability of type 1 error is called the level of significance. This is called the level of significance. And this is a prescribed level of committing a type 1 error. There is this level of significance which is there. So basically, probability of type 1 error is the level of significance, and it's an exogenously prescribed value. So the level of significance is nothing but it prescribes a tolerable amount of chances of committing a type 1 error. So how much of a type 1 error, or to what extent of how much of commission of type 1 error is permissible. So this is an exogenously provided value. This provides the benchmark to a statistical test. So it is this level of significance. So that is the level of significance. And there are generally two levels that we generally work on. One is a 0.01, or as we call the 1% level of significance. And the second and the most standard one is 0.05. But since business data and business results needs to be very accurate, right? Therefore, we generally do not conduct testing at 5% level, but we try to conduct it at 1% level. Obviously, depending on the existence of the data or on the data size of it, right? So therefore, there are two chances. One is 1% level of probability, 1% level of significance. The other is the 5% level of significance. So this 5% level of significance specifies the extent of tolerable error that we can commit in a particular test, right? So this is precisely what the level of significance is. So this level of significance is very similar to this permissible extent of error defined over here, right? So there is a rejecting a true null hypothesis, right? So the type 1 error is nothing but it is said to occur when we reject a true null hypothesis. So basically, say the difference was insignificant, but we considered the difference to be significant, right? Now, there is also an actual probability of committing a type 1 error. Like over here, we have a benchmark error, benchmark extent of error, and also a kind of, what should I say? There is also this kind of actual error that is committed during the test. So similarly, over here we will have a type 1 error, which is a exogenously provided probability of type 1 error. On the other hand, what we are trying to do is we are trying to kind of so what we are trying to do over here is kind of uh, specify a exogenous level of commission of type 1 error, and we are also defining a measure or an actual measure of committing a type 1 error, right? And then we'll compare the two and we'll decide that whether a difference is significant or not, right? So if you look into that example of this mathematics test that I had given, so if the actual error is lower than the permissible error, then the actual then it implies that the test statistic or the actual value of the statistic is greater than the critical value. So if I consider in that mathematics example, if I consider the actual mass obtained as the statistic over there and 40 as the critical value of the statistic, then we see that the critical value of the statistic is constructed corresponding to a given provision of error, and the actual marks obtained is also contingent on also contingent on the certain chances of committing an error. So over here, what we get to see is that there is a cutoff marks which is 40. So that 40 is nothing but our critical statistics, or the critical value of our statistic. The second is 25, which is the actual marks obtained by the student, or 55, which is the actual marks obtained by the student. So that is our test statistic. So what you get to see is, when you are looking into this test, when you want to understand this particular, when you want to identify whether a difference is significant or not, you have to define it with respect to some chances of error, right? And when you define the chances, there would always be a permissible extent of error, and there would be an actual error. Now, depending on whether the actual error is more than the permissible level extent of error or not, you will be taking your testing decisions. Right. So over here, so let's see that how does that concept of mathematics test, how does that come out and like match up to what we are trying to do. So over here, let's draw a straight line. So let's take this case that this is mu. This is the actual value of mu, right? And over here, what I have is x bar, right? Now, if I consider this difference to be significant, there is always a probability that I will commit an error, right? So if this is the actual value of the test statistic and this is the population mean mu, and if I consider this difference to be significant, then there is always a probability that I might be committing a type 1 error. So the probability that I might commit a type 1 error is an actual probability that I can commit a type 1 error, because this difference is based on the actual differences, the actual difference of the statistic from the population parameter mu. Therefore, this probability, or this actual probability of committing the type 1 error, is said to be p, or this is what is the p value that we have, right? Now I need to benchmark. Now, how do I know that that this is I mean, whether this error is a negligible error, or is it a very high chances of committing a type 1 error? How do I know that? So for doing that, I need to have a critical distance, right? Say the critical distance is this. So this is the critical distance. Now observe that. Now this is the distance, right? So from corresponding to this, this distance, there would also be a chance of committing a type 1 error, right? Now, the chances of committing a type 1 error corresponding to this distance is either 5% or 1% because that will be exogenously given, right? So I say that the distance between mu and x bar c, so this is 5%, right? And over here, what I have is the p value, right? So if I see that this p value is closer, so basically, if I see that the p value or the actual probability of committing the type 1 error is less than the level of significance, we denote this level of significance by alpha, then we say that H naught is rejected at alpha level of significance. Level of significance. But in the example that I have shown you, right? In the example that I have shown over here, H naught is not rejected at alpha level of significance. Why? Because over here the actual value of x bar is very close to mu, is relatively closer to mu. That means if I consider this difference to be significant, I will run relatively higher chances of committing the type 1 error than if I consider this difference or the critical difference to be significant. Therefore, the probability of committing the type 1 error or the actual probability of committing the type 1 error over here is much greater than 5%. So in this case p or the actual probability of committing the type 1 error is greater than 0.05 or 5%, and hence the h naught over here is accepted at at alpha level of significance. So therefore h0 is accepted, 0 is accepted at alpha level of significance, at alpha level of significance, right? So is the testing procedure clear to us? Go through it, think through it, check whether you understand all the concepts or not, then we'll carry on again. I'm going on mute. If you require anything, put it in the chat box. I'll reply it, or if required, I'll unmute myself and I'll answer it, right? Just take the next 2 minutes, 2 to 3 minutes, go through this discussion, whatever we have said, and then we'll carry it out. Then we'll take it up. Okay. So is the decisioning process clear? So are we clear about this idea of decision? So concept of p-value, the level of significance, type 1 error. Are we guys clear on this? So basically what happens over here is, so what we saw that when we compare the actual probability of committing the type 1 error, right, to the prescribed or the pre-decided level of, so over here it's basically the idea is that when we are trying to decide this, when we are trying to assess whether the borrower I mean whether difference is significant or not, what we are doing is we are comparing the actual probability of committing the type 1 error to the, the pre-decided or the benchmark level of committing the type 1 error, right? So this is what uh, we are comparing in order to, you know in kind of, what should I say, so basically we compare the actual level of, the actual probability of committing the type 1 error and the benchmark level of the probability of committing the type 1 error, and from there we decide whether a difference is significant or not. So over here, if we just want to summarize, right, the testing rules, then it will be something like this: that H naught is, say it's like some beta equals to zero or something like this, right? So beta equals to zero versus the alternate hypothesis. H naught beta equal to zero versus the alternate hypothesis beta not equals to zero, right? So over here, that is if P is less than alpha, that is if the level of significance is, I mean if the p-value is less than the level of significance, that is the actual probability of committing the type 1 error is much lower than the actual probability of committing the type 1 error, then H0 is rejected at alpha level of significance. H0 is rejected at alpha level of significance. if p is greater than alpha, so that is if the actual probability of committing the type 1 error is greater than the level of significance, then h0 is accepted at alpha level of significance. Okay, so this is what the very basics of statistical testing is. Now, depending on the business problems, there are multiple kind of statistical tests. There are multiple kind of statistical tests. One is a single mean test. Then there are mean difference tests. Then there are tests to assess the association between two categories, assess the correlation between two with continuous variables, and so on. There is a whole set of testing procedure which is involved, right? And in today's discussion, we'll take up each of these discussions or each of these topics one by one. Uh, so the first kind of tests that we can talk about over here is the single mean test. It's the single mean test. It's a single mean test. The second set of tests that we have over here is the mean difference test. The mean difference test. So the next part that we have over here is, so why we have the mean difference. So one test is the single mean test. Then we have the mean difference test, right? Within the mean difference test, we have it for paired samples and independent samples. Then we have, the test like the chi-square test, the chi-square test. Then what we have is the F test, right? So this is a single mean test, mean difference test, chi-square test, F test, and it goes on like that, right? So there are a few important tests. So over here we will be talking about the chi-square test. We'll talk about the single mean difference, and chi-square F test. And each of these tests have their own reasons or has a own logic of being performed. Now within the mean difference test, there are two types of mean difference tests that happen. One is two independent sample for two sample tests. Okay. So a two sample test which is there. The two sample test. So where there are two groups of samples, right? And this is for multiple sample tests. More than two samples. This is multiple samples. This is the multiple sample test. Now for the two sample test, now within multiple sample tests, we have what we apply is the ANOVA, which is called the analysis of variance. This is ANOVA. And within so for multiple sample tests we apply ANOVA. Now for when I talk about ANOVA, there are two types of ANOVA. One is a one-way ANOVA, and the second that we have is a two-way ANOVA. What we'll have is one-way ANOVA and a two-way ANOVA. The next part is, so when I talk about two sample tests, there are two types of two sample tests. One is an independent, two independent samples, and what we have over here is two dependent samples. Two dependent sample tests, right? And most of these tests are done using parametric tests. So both ANOVA and the t-test, which is actually applied over here, or for the single mean test. So whatever all the tests that are applied for here is the t-test, right? And the one that we have over here also for ANOVA. So both ANOVA, t-test, both of these tests as well as chi-square and f-tests. So all these test procedures are parametric tests. So these are all kind of parametric tests. So what is a parametric test? A parametric test is a test which works under the assumption that the variable x follows the variable on which you are doing the testing procedure. That variable follows a normal distribution, right? So over here what we have is the parametric test. Right. So basically, this all these tests are based under the assumption that the x variable for which we are doing these testing procedures, right? So these variables are normally distributed with the mean mu and variance sigma square, right? And the next step would, and the next stage of this discussion would be to take up each test one by one and see how they are actually done. What exactly is the way, what exactly is the technique of performing these tests, right? So I'll not start these tests afresh today because we'll not be able to complete even one of them. We'll start off talking about these test procedures in tomorrow's discussion. So tomorrow we'll complete this part, and with this, the statistical inference will come to an end. And post that, we start off with scorecard development. So when we start off with scorecard developments, or talking about scorecards, business products, and stuffs like that, that is where you come to see how these statistical measures are getting interrelated with those business problems. So to understand the interrelation between these two domains is the first and the most important criteria. It is only after that we can think about the next stages of development and so on. Right? So this is what we have the next. I mean, this is what we have to cover in the next class. Thank you. So, in case of any questions or any doubts you want to clarify with me regarding testing procedures and stuff, feel free to get back to me. Bye bye.